Hi, I am Shivani of CSCD section. I'm gonna talk about theory of computation, deep optimization for spectrum repacking. Introduction: many devices, including broadcast television receivers, and this paper builds in part an conference publication by the same authors solving the station repacking problem, which was published at AAI 2016. Permission to make digital or hard copies of all a part of this work for personal a classroom use is granted without fee, provided that copies are not made or distributed for profit or commercial advantage, and that copies bear this notice and the full ci- citation on the first page. The station repacking problem. We now describe the station repacking problem in more detail. Each television station in the US and Canada there exists a large body of prior work that investigates the use of algorithm configuration to design novel algorithms from large parameterized spaces, some of which indeed we have co-authored. We believe, however, that the work described in this paper is the most conventional application of such techniques to date. Much of the literature must mention focuses algorithm designs methodology. Most work in the latter vein either addresses the much broader problem of algorithm synthesis or defines the overall approach only implicitly. The most prominent exception is programming by optimization. However, it emphasizes connections to software engineering and does not limit itself to parametric design spaces. Similar problems have been studied in other contexts, falling under the umbrella of frequency assignment problems. See example for a server and a discussion of applications to mobile telephony, radio and TV broadcasting, satellite communication, wireless LANs, and military operations. We are not aware of other published work and that aims to optimize feasibility checking in the intensive auction selfing currently assigned to a channel that ensures that it will not exclusively interfere with other nearby stations. A deep optimization approach, as we show in our experiments of the show self servers, could not solve a large enough fraction of station repacking problems to be effective in practice. To do better, we needed to a customized algorithm optimized to perform well on our particular distribution of station repacking problems. We build our algorithm via the deep optimization approach, meaning that we aim to use our own insightly only to define design ideas that showed promise, delegating the work of combining these ideas and evaluating the performance of the resulting algorithm on realistic data. The design space. Our first task was thus to identify a space of algorithm designs to consider. This was not just a pen and paper exercise, since each point in the space needed to correspond to runnable code. We focused on encoding station repacking as a proportional satisfiability problem. The SAT formalism is well suited to station repacking, which is a pure feasibility problem with only com- combinatorial constraints. We did not investigate such alternatives in depth. The SAT reduction is straightforward. Selective solvers, perhaps the most important top level parameter, determines which SAT solver to run. Each course, each solver will have its own parameter space. Other parameters will describe design dimensions orthogonal to the choice of solver. As we will discuss in what follows, the SAT community has developed a very wide variety of solvers and made them publicly available. using the previous solution while adapting CLASP and SAT Einstein to station repacking. Data yielded sustainable performance improvements. Neither reached a point sufficient for deployment in the real auction. To do better, it was necessary to leverage specific properties of the incentive auction problem rather than committing to specific speedups. We exposed a wide variety of possibilities via further parameters. We began by considering two methods for taking advantages of the existing of a partial assignment. Problem simplification. Next, we considered three pre-processing techniques that can simplify station repacking problems. First, we added the option to run the arc consistency algorithm, repeatedly pruning values from each station's domain that are incompatible with every channel on a neighbor station domain. Second, we enabled elimination of unconstrained stations. A station is unconstrained if given any feasible assignment of all of the other stations in S/S. There always exists some way of feasibility repacking. Containment caching. Finally, we know that every repacking problem will be derived from a restriction of the interference graph to some subset of S. We know this graph in advance of the auction. This suggests the possibility of doing offline work to pre-compute solutions. However, our graph has 2,990 nodes and the number of restricted graphs is thus 22,990 to 10,900. Thus, it is not possible to consider all of them offline. Searching the design space. Overall, our design space had 191 parameters nested as much as 4 levels deep. We now describe how we searched this space to building a customized solver, identifying a set of parameters that optimize a given algorithm's performance on a given dataset is called algorithm configuration. There exists a wide variety of algorithm configuration tools. We used a sequential model based algorithm performance approach of interleaving random sampling and the exploration of algorithm designs that appear promising based on a learned model. Data from auction simulations. During the development of SATFC, the FCC shared with us a wide range of anonymized problem instances that arose in auction simulations they performed in order to validate the auction design. These formed the training set we used in the deep optimization process when constructing SATFC. These simulations explored a very narrow set of answers to the questions of which stations would participate and how bidders would interact with the auction mechanism. They do not represent a statement either by us or by the FCC about how these questions were resolved in the real auction, and impossible to the guarantee that variations in the assumptions would not have yield conceptually different problems. Runtime performance. We now evaluate SATFC's performance by contrasting it with the various off-the-shelf alternatives. The FCC's initial investigations included modeling the station repacking problem as a mixed integer program and using off-the-shelf solvers paired with problem-specific speedups. Unfortunately, the problem-specific elements of this solution were not publicly released, so we cannot evaluate them in this article. Instead, to access the feasibility of a MIP approach, we can run what are arguably the two best performing NIP solvers, CPLEX and Gurubane, our test set of 10,000 non-trivial instances. Impact on economic outcomes. Greater New York City simulations. National simulations. We are more interested in economic outcomes at the national scale, even though we could not simulate VCG in such a large setting. Conclusion. Station repacking in the intensive auction is a difficult but important problem, with progress translating into significant gains in both government expenditure and social welfare. We designed a customized solution to this problem using an approach we dump deep optimization. Specifically, we drew on a large parameterized design space to construct a strong portfolio of heuristic algorithms, SATFC, an open source solver that was used in the real auction. Acknowledgements. We gratefully acknowledge support from auctionists and the FCC, valuable conversations with Paul Milgrom. References. That's it. Thank you.